CBE 340, Mass Transfer and Separation Processes, Spring 2024, WAMB M307, Monday, Wednesday, Friday, from 12:40 through 1:30 p.m. The instructor is Professor Steve Abel. His office hours are Wednesday from 2 to 3 p.m., Daughtery in 314, and Fridays from 3 to 4 in Daughtery 327. We have teaching assistants, Greg, Ali. Mass transfer is the process by which mass is transported by diffusion and or convection. It is a cornerstone of chemical engineering and is the third pillar of transport phenomena. You have already studied momentum and heat transfer in CBE 340. We will study mass transfer from both fundamental and applied perspectives, ranging from molecular to continuum descriptions. Mass transfer and thermodynamics provide the framework needed to analyze separation processes, which are also essential in chemical engineering. We will study ways to separate mixtures of chemical species using single equilibrium stages, multi-stage cascades, and absorption stripping. You will continue to study separation processes in further classes. I will post a running list of topics and reading assignments under Syllabus on Canvas. I will also record lectures and post them to Canvas, although this is intended to supply as supplemental study material and not as a primary means of viewing the lectures. The textbook required for this course is Cedar, Henley, and Roper, Separation Process Principles with Applications Using Process Simulators, 4th edition. We will cover the first 6 chapters of the book, plus supplementary topics. This book is also used in CBE 445, Separation Process Technology. Note that it may be useful to use materials from CBE 240 as a reference. The assessment: we will have approximately weekly problem sets, 3 in-class midterms, and a final exam. The homework is 17%. You are welcome to work together to solve problems, although you are expected to write up your own solutions independently. And working through problems independently and understanding the process should prepare you for exams. All homework assignments will be submitted as PDF documents through Canvas. The midterms are 17% each, and the final exam is 30%. Exams will be held in classroom. Other assignments and materials will be posted on Canvas. Here's the copyright information. The instructor of this class owns the copyright to the syllabus, hands-out, assignments, quizzes, and exams associated with the class. All presentations developed by the instructor as well as the instructor's lectures are also protected by copyright. Whether these presentations and lectures are delivered live in class, shared through Zoom or other video conference platforms, or uploaded to Canvas or similar sites. Sharing any of this material without the written permission of the instructor is a violation of copyright law and therefore is a violation of university's policy on acceptable use of information technology resources. The policy states that students will not commit copyright infringement, including file sharing of video, audio, or data without permission from copyright owner, and that file sharing is a violation of the student's code of conduct. Such violators will be reported to the Office of Student Conduct and Community Standards. Course learning objectives. At the conclusion of this course, students should be able to 1. Compare and contrast mass transfer by molar diffusion and convection. 2. Use Fick's law of diffusion in a mass balance for a simple geometric configuration in order to estimate mass transport rates in a binary system at steady state. 3. Estimate the time required for diffusive mass transfer to take place in simple geometries in binary systems. 4. Explain the difference between equimolar counter-diffusion and unimolar diffusion and identify physical situations that approximate these two conditions. 5. Calculate values for binary diffusion coefficients in gas and liquid phases at specified conditions using standard models and correlations. 6. Use separation of variables to solve the diffusion equation for simple geometries. 7. Explain the difference between individual phase, gas phase or liquid phase, and overall mass transfer coefficients and between local and average mass transfer coefficients. 8. Calculate values for mass transfer coefficients for specified values of the Reynolds number and Schmidt number. 6. Explain the concept of a film model for mass transfer. 10. Calculate pressure as a function of composition at vapor/liquid equilibrium using fugacity and modified Raoult's law for non-ideal mixtures. 11. Construct the T-X diagram for a binary mixture given the liquid pressure as a function of temperature. 12. Explain the concept of stage-wise operation as applied to absorption, stripping, distillation, and liquid extraction. 13. Design tray and packed towers for absorption or stripping processes. 14. Use one-dimensional material balance on an elemental volume to derive an equation for the steady mass transfer rate in a packed bed. 15. Explain the height of transfer unit HTU and number of transfer units NTU, concepts as applied to packed tower separation processes.